Hi guys, welcome to my talk. This talk is HSM, a hybrid slowdown model for multitasking GPUs. GPUs are changing the world now, from the mobile phones to desktops to data centers to supercomputers. GPUs are widely used to accelerate a wide range of applications. However, if you only execute one application on GPUs, it has very poor resource utilization. For example, if you only execute a compute-bound application, for these applications, they usually have very few memory accesses, so the resources of memory are underutilized. On the other hand, if you only execute a memory-bound application on GPUs, these applications usually have a lot of memory accesses. In this case, the SMs are often stalled because of the memory access, and the compute resources are underutilized. To solve this problem, people began to use the spatial multitasking. In spatial multitasking, two applications with different characteristics co-execute on GPUs. In this case, the memory resources and compute resources are well utilized. However, in multitasking GPUs, we have the resource contention. If you only execute a single application on GPUs, there is no resource contention because this application it can occupy all the resources in GPUs. However, if you co-execute two applications on GPUs, there is resource contention between these two co-executing applications. They will compete for the SMs, not bandwidth or memory bandwidth. In this case, the performance in multitasking is less than the performance in single tasking. The cloud providers require the fairness and the QoS support in multitasking GPUs. For the fairness support, it is the co-executing applications have equal slowdown. For the quality of service QoS support, people usually preset a target and try to make the application meet the target. Slowdown is the performance in single tasking divided by the performance in multitasking, which is larger than 1. Predicting slowdown plays a critical role in fairness and QoS support. Look at the slowdown formula, which is the performance in single tasking divided by the performance in multitasking. The performance in multitasking is easily obtained through the online profiling. However, we don't know the performance in single tasking when the application is executing in the multitasking mode. How to predict the application slowdown? In this paper, we propose the hybrid slowdown model to do this. First, let's take a look at the white box model and the black box model. The white box model, it uses architectural insights to do the slowdown prediction to try to analyze the performance hazards caused by different architecture stalls like the pipeline stall, the cache misses, or the branch prediction. For the white box model, it usually has very low hardware cost. However, it is very difficult to use white box model to capture the overlap effects in GPUs. Because the GPUs, it has very high thread level parallelism and memory level parallelism, so many performance hazards overlap with each other. For the black box model, it uses the ML to learn the features of GPUs and also the applications. It has very high hardware cost because it needs storage to store the layers of weights, which is usually megabyte. The good part is that the black box model can capture the overlap effects on GPUs because it only uses the machine learning to learn the features. In this work, we propose the hybrid slowdown model to benefit from both worlds. It uses the architectural insights to reduce the hardware cost. Meanwhile, it uses the machine learning to model the non-trivial overlaps. In this case, HSM can quite accurately predict the GPU slowdown with a very low hardware cost. This is the overview of HSM. It first uses a classifier to classify the kernels into the compute bound or memory bound, and then predict the slowdown for each type of kernels. First, let's take a look at the compute bound kernel. This is the performance changes with the count of SMs. It's very clear that for the compute bound kernels, their performance increases linearly with the SM count. So we can use the SM count to do the slowdown prediction. Here is the slowdown model. The slowdown is the SM count in single tasking divided by the SM count in multitasking. The SM count in multitasking, which is obtained during execution. The SM count in single tasking is all the SMs in GPUs, which is known. So in this case, we can predict the slowdown of compute-bound applications. Next, let's look at the slowdown prediction for memory-bound applications. For memory-bound kernels, their performance first increases but then saturates very quickly with the increased number of SMs. This is because these kernels usually care about memory bandwidth. When the SM count increases, their performance first increases, but when the memory bandwidth reaches the maximum value, their performance does not change. The right figure is the normalized bandwidth utilization with the increased SM count. It's very clear that the bandwidth also increases, but then saturates with the SM count. Because the performance trend and memory bandwidth trend have very similar curves, so we can use the memory bandwidth utilization to predict the slowdown. The slowdown is the bandwidth utilization in single tasking divided by the bandwidth utilization in multitasking. The bandwidth utilization in multitasking is obtained during execution. The difficult part is how to get the bandwidth utilization under single tasking. We make two key observations in the work. The first is that the row buffer hit rate determines the memory bandwidth utilization. The left figure is the organization of an HSM channel. It has multiple banks. For each bank, it has a row buffer, which is used to store the last accessed row. So if the new coming accesses the same row, it has a row buffer hit. On the other hand, if it accesses another row, which is not in the row buffer, it has the row access miss. Because GPUs, it has very high level memory level parallelism, so the bank level parallelism is maximized in GPUs. In this case, the row buffer hit rate determines the idle time of banks and is the only factor determining the memory bandwidth. The second observation is that row buffer hit rate is similar under single tasking and multitasking. This is because the first ready, first come, first service used in memory controller always prioritizes the row hit requests from the same application. In this case, the row buffer hit rate in single tasking is very similar to the row buffer hit rate in multitasking. So based on these two observations, we can do the slowdown prediction of memory-bound kernels. Look at the slowdown formula, which is the bandwidth utilization of single tasking divided by the bandwidth utilization in multitasking. The bandwidth utilization in single tasking is C1 multiply row buffer hit rate in single tasking plus C2. C1 and C2 are used to reflect the linear relation between row buffer hit rate and bandwidth utilization. Because the row buffer hit rate in single tasking is similar to the row buffer hit rate in multitasking, thus the formula becomes C1 multiply robust hit rate in multitasking plus C2. After talking about the slowdown prediction for compute bound and memory bound kernels, next let's take a look at the classifier, which is used to classify the kernels into compute bound and memory bound. We calculate the bandwidth demand of the kernels by using the executed instructions, memory accesses, and operating frequency. We calculate the bandwidth utilization potential by using the theoretical bandwidth of the GPUs, which is also the maximum bandwidth, and also the robust hit rate. If the bandwidth demand is larger than the bandwidth utilization, it is a memory-bound kernel. On the other hand, if the bandwidth demand is less than the bandwidth utilization, it is a compute-bound kernel. The total hardware cost of the model and the classifier is only 0.8 kilobyte, which are the counters to record the architectural events. Based on the HSM, we propose the SM allocation policies. We divide the execution time into epochs, where each epoch is 500 kilocycles. In the end of each epoch, we predict the slowdown and reallocate the SMs. We propose the HSM fair to do the firmness support, and we propose the HSM QS to do the QS support. Next are experimental results. We use GPU sim to simulate GPUs. We use Remulator to simulate HBM system. We combine these two simulators together. We simulate the water-like GPUs, which has 80 SMs and 900 GB per second memory bandwidth. We use 15 applications in the evaluation. It's very clear that HSM has very high prediction accuracy. On average, the prediction error is only 6.8. We compare HSM with the previously proposed white box model DIS and black box model SIMT. It's very clear that HSM outperforms the white box model and black box model. For the fairness-aware SM allocation, it achieves 84% fairness on average. This is because HSM can predict the slowdown, and then it can try to reallocate SMs to meet the fairness target. The QS-aware SM allocation meets the QS target for all applications. We preset the 0.8 QS target, and HSM QS can meet the target for all workloads. On the other hand, DIS-based QS SM allocation or SIMT-based SM allocation cannot meet the QS targets of some applications. We also compare the HSM fair with the memory bandwidth partitioning. HSM fair also outperforms previous approaches based on bandwidth partitioning. It's because the memory bandwidth partitioning technique only partitions the memory bandwidth and it does not change the compute resources. That's why it performs worse than the HSM fair. We also did additional analyses in the paper, like the fairness threshold, how to train the Black's model, the memory controller parameters. We also use GDDR5, and we also adopt for program workload mixes. HSM performs well for all configurations. Details can be found in the paper. The white box model and the black box model have different advantages. White box model, it has very low hardware cost. Black box model, it can capture the overlaps. HSM benefits from both worlds, which has a low cost. Meanwhile, it can capture the overlap effects. We propose two SM allocation schemes based on HSM. We propose HSM fair to improve fairness, we propose HSM-QS to meet QS target. For some results, HSM, it has 6.8 prediction error with 0.8 kilobyte cost. HSM Fair achieves 84.1% fairness, and HSM QS can meet the QS target of all applications. Thanks for listening.